Thank you. So I'm going to get to the shallow end of learning. I'm sure you've all been stuck in the deep end for too long now. So in this talk, we're going to look at a recommendation task, which is very prevalent in the web industry, but not just in web industry, but in pharma or as simple as just a restaurant recommendation to your friend. So as an example, so you have a user who comes into your recommend system, and you have a bunch of items that you recommend. So the user first chooses an item to buy and maybe another one, and then you get the feedback in the form of a click, or he's added to the cart, or you get a payment for this. And then you have a new user coming in, and you have the same list of items that you sort of show, and then she picks a completely different item, and you get a new feedback for this particular user. So this is a typical task in many businesses now. So for example, Amazon is a direct example of this, book recommendations or movie recommendations, but then all online media or shopping companies and your streaming companies for movies and music. And then you have your social networks where you recommend jobs or friends or contacts that you can add. Or it could be online dating, which is like a multi-billion-dollar industry now. Or it could be a news website which wants to recommend articles to you to improve their click-through rate and user engagement. Or it could be personalized medicine where the treatment is tailored according to the needs of the final user and of the patient, and not necessarily one single treatment for all. So all of these fall under the same umbrella of recommender problems. And in all of this, there's a common theme, which is we need to know how the reward function behaves according to the item that you're recommending, according to the user's needs, and according to the list that is actually shown initially, the ones that you're experimenting with. So this is a common theme across all these problems. And there are many popular techniques which hope to predict this reward. But then all of these existing techniques mostly try to predict for a fixed data set. So there's a bunch of user interactions. So you have these items, and then you have users coming in, and you have some history of interactions. And based on this, you try to predict one shot the reward for all the items and users that are not yet seen. But this is not really true. It's a very simplifying assumption because it's not true in any of these applications that we have seen. What really happens is this: the users and the items are many and dynamic. You have new users coming in about whom you know nothing, and you have the inventory changing all the time. And also the preferences change. People hear a recommendation from a friend. Their preferences change outside your system. So you have no way of keeping track of this. And hence, estimating all the rewards for all the users and items is a very hard task. And not just hard, it's wasteful. Let's say that out of 10,000 books that are there, or 1 million books that are there on Amazon, you're going to read maybe 1,000 in your lifetime, 2,000. Why would you want to estimate all the rest of the items? Or let's say there are movies that you would rate 1 out of 10. How does it matter whether you rated 1 or 2? Why do you want to know the exact rating? You really care about only those items for which there's a potentially high rating that you're going to receive. So can we use this insight somehow? Instead of having to compute the feedback for all the items that are there, can you only compute for those items for which a potential high rating is possible? So here you run into this explore exploit problem, where you want to experiment with your user to see what kind of things that he likes. And as and when you're learning, you also want to improve your recommendations along the line. So it's an interactive system. And this explore exploit dilemma has been solved by this concept called multi-arm bandits. So this concept is you walk into a casino, and then you have many single-arm slot machines. Each slot machine has a payoff. So you can go to a machine, invest some coins, and get a payoff. Now, if you're given a fixed amount of budget, how do you make the most out of this budget? So you have to go to the machine which has the best payoff. But how do you know which machine has the best payoff? You have to repeatedly play across these machines, figure out which one seems to give you the best payoff, and then invest all your remaining money in this one. That's how you maximize. So here you're experimenting with different machines, but also finally trying to figure out this one machine which will give you the best payoff. So many of the early approaches to solving this problem, which arose in experimental design, required that the number of iterations or the total budget that you have is larger than the number of arms that you have to experiment with. So you have to play, for instance, in this slot machine, every slot machine at least once, because the one that you missed could have the maximum payoff, and then you're going to do much worse than doing this. So you need to play at least everything once, and multiple times in order to count for statistical significance. And then you can get guarantees if this assumption holds, right? But obviously, as the number of arms increases, the performance decreases. And here by arms, I mean the number of items that you can experiment with. But this is definitely not true in any of the recommender system problem that we saw, because here the number of items are much, much larger than how many interactions you have with the user. For 1 million items, you probably have 100 interactions with the user. And the other problem with some of these early approaches was that they were not contextual. So they could not be tailored based on an individual user. So for each user, you had to learn a new instance of the problem. Now, the modern approaches were what we call learning meets bandits. Here, we want to generalize some of the results of the experiments to unseen items as well. Let's say we experiment with a few items, and then we want to somehow capture similarity of item and use this knowledge to sort of predict what you would get out of these new items that are as yet unseen. So, but for this, we cannot get anything for free. We have to make some assumption on the reward function. So as we saw, the reward depended on the user, the item, and the list of experiments that you have done, right? So some of the assumptions, simplifying assumptions which were made on this reward function, and they perform much better on real-world tasks. And in our work, we also pursue this approach. So again, getting back to the problem setup, you have this user who comes into your system. So let's say he's characterized by certain user attributes. This could be age, sex, any of the demographics that you want. And then you have this huge item set from which you can select a list of recommendations. And you have this list, you have B slots in which, so let's say Google, for instance, has 10 results for a search query, or Amazon shows 20 related books for a single search, for instance. So this B is the number of slots that you have to show the ordered list for. And the entire list at time t is LT, and each individual item is ST. And then once you get the feedback, it could be a binary vector, which just says click or no click, buy or no buy, or it could show the value of what is the purchase amount, for instance. And what we want to maximize is across all interactions with different users. So at time t, this is our user. So at different users, and across the entire list, you want to maximize the payoff that you get, the reward that you're getting. And for technical convenience, we also compare ourselves. Instead of maximizing this, we could minimize this hypothetical optimal, which we can never compute, but we can say we want to compare very well against this hypothetical optimal. So this is just for technical convenience. And we call this term the regret of your algorithm. Now, in our approach, what we do is that we propose this CGP rank. It uses a Bayesian model for rewards, and it efficiently shares the rewards across the items based on some similarity notion, across users, again based on similarity because we have the user features, and across positions along the list. And how we do this is, so we still need to predict this whole reward function, but we assume that items do not influence items in other positions. So we say that you would get the same feedback on a particular book if it was shown with some other set of books. Sometimes you might get a boosting effect because of related books, or we just discard that assumption. We just discard this factor. So then this reward function factorizes as the relevance term, which is how important or how effective is this item for this user, and a separate position term, so which is the position effects. When you're showing a list of items, the chance that despite being less relevant, the first item might get more clicks. That's a very well-known phenomenon on the web. So we separate out in this way. And how do we share across positions? So let's say we have got the clicks for these books on different positions, 1, 2, 3, 4. And now we want to reorder. It looks like despite being in the third position, this book is very, very close to the second one. So we want to reorder a bit and see what would be the new click-through rates. For this, we have the position weights which are estimated in an unbiased fashion from the logs. So across all items, if you compute what are the total clicks in the first position versus in the second, in the third, you can get these similar numbers which says this is the position effect of each of these positions. And then all you have to do is some simple math which tells you finally what can be the expected reward in the new position. And this is unbiased. It's statistically sound to do this. And how do we share across items and users? So we want to capture this notion of similarity. So let's say the first book of Harry Potter is very similar to the sixth book, right? Somebody who likes this is very likely to like this. But it's also somewhat similar to the series, fantasy series. So say it's very similar to, somewhat similar to Lord of the Rings, for instance. But then somebody who likes Hemingway is never going to write like the trash that Dan Brown writes, for instance. So we want to say they're not similar at all. So these are the kind of assumptions that we want to capture. Intuitively, it makes sense. So how we manage to do this is, so let's say there's a bunch of users who like, we want to say that their preferences vary smoothly. Given two similar books, their preferences would also be similar for these two books. And then there's a new user who comes in who's characterized by a completely different function, who's very dissimilar to this set of users. Then he has another set of smoothly varying preferences over the items. So how we capture this is by the concept of Gaussian processes. Gaussian processes are distributions of functions, of reward functions in this case. So here we say that these are all likely functions because they are smooth over your choice, your space of choices, right? And this is unlikely because it varies wildly. But this is before any data was observed. Let's say we observe some data, which is clicks on books or ratings that were given to movies. So some of these remain likely because they obey the data, whereas something else, because they do not obey the data, becomes unlikely. But not just that, the ones that obey the data but vary wildly over the data, which is overfit to the data, for instance, these again remain unlikely. And the advantage of using this is that analytically we can get closed form solutions, and it also allows to represent uncertainty in our ratings. We are not just saying that you can expect a rating of 5. We also give you a confidence around this. And we care about the marginals. So given a new point at which you want to predict the rating, we also can give you the uncertainty around. It's Gaussian, so it's very easy to compute these things. And the key component here is the kernel function or the covariance function, which captures the similarity between items or users for that matter. So this is the intuition when you want to select just a single item. The boundary, the gray boundary is the confidence around your predictions, and the black line is the mean of the current predictive function. So the selection rule that selects a single item is basically the mean, the current mean, plus some multiple of the standard deviation. And this is for a single item, and what we want to do is select lists, not just single items to recommend. So here, let's say, again, you have a bunch of user who comes in. If you have no observations, then all books are equal for you. But let's say you have some prior observation. Maybe the user has bought this book earlier or given the rating in one of your feedback forms. So then you know that this user probably likes this book. And here you can shrink the uncertainty around the rating for this book, not just at that book, but also at other related books, right? And then now let's say you want to select, you want to recommend 2 books to this user. So the first item is again selected according to the selection rule that was just explained. But then we cannot wait for the feedback. The earlier video that you saw was for selecting single items. Here we cannot wait for the feedback. We have to select the second book as well. So what we do is that we hallucinate the feedback as the current mean. And this helps us to shrink the uncertainty around the books. And now you can update this model and pick using the same rule again. So now we have selected 2 books. And once you get the correct feedback, you can feed that back to the system to shrink the confidences further. Or the uncertainties further, rather. So this is just a formalization of what I just explained. It's not very important. And it's not just, it has very strong theoretical guarantees. We can prove some bounds on this. What we say is that the essence of this is that the regret grows sublinearly. And this is a good thing. And the other thing that is surprising or counterintuitive is that as you increase the list size, basically, instead of recommending 10 items, if you want to recommend 100 or 200, under very mild assumptions, we can show that having to select more items is a good thing. And it's counterintuitive because the list size grows exponentially. Your number of lists that are possible grows exponentially along with list size. But because of the way we share feedback across positions, having to select more items the algorithm becomes better and better at selecting more items. So, and not just theoretically, experiments we carried out on 2 different data sets. The first one was by a master's student who worked at Google, who implemented this algorithm on the logs of Google Books, recommendations and the clicks on Google Books. So we had 42 days of logs, and we were given, basically the user is currently browsing a particular book, and you want to select, you want to show a list of books to recommend. We already had this log. What we did was play back this log to the algorithm. We didn't have access to the data set itself outside, but because the master's student was at Google, he was able to run this as part of his thesis. And the other one was because of this data set that Yahoo released, which was the news article recommendation data set. This is available for free for people who request for it. And this had like 10 days of user log on the Yahoo News front page property. And basically this data set is an unbiased method or unbiased way to test bandit algorithms. And we had 45 million user interactions with about 271 articles. So the feedback was available only for single selection, but there are ways to extend this to multiple selection feedback as well, which is what we used in this paper. And the questions that we asked was this principled sharing that we talk about, how does it help across items and context, where context is the user, items is the recommendation task that you have, and across positions. And the other question, important question is, our algorithm, can it perform well against an existing algorithm? Something which was tuned well in the industry, has been running and making money for some company. Can we beat that algorithm real time? So sharing across items, here again, you can see that ideal is the optimal hindsight policy. So this is not a real policy that you can implement. It's this hypothetical ideal. And you can see that our algorithm outperforms existing good algorithms. And across contexts, again, we are doing better than most of the existing ones. And this is the counterintuitive effect that I was talking about. You can see that as the batch size increases from 1 to 2 to 4 to 8, the regret keeps going down, which means our algorithm is getting better and better at recommending larger lists. And finally, this is the comparison to the existing algorithm at Google for the Google Books dataset. So we were able to give a 11% improvement in clicks, a predicted 11% improvement. This was never run real time. But on the logs, on the last 10 days or 42 days of log that we had, we were able to get 11% increase in clicks. Thank you very much for your attention. And I welcome questions and also collaborations and more data sets from you guys, if possible. Thank you.
Are there any questions?
Yes.
I might have missed it, but how are you testing these? How are you testing this? The benchmarking shows in the graphs.
So when you have the logs, you have interaction of the user with the items that were already shown. Now, there is some techniques available for offline evaluation. What you can do is you can assume that instead of showing what you actually showed, if you had showed something else, what would have been the feedback? And this you can learn from the logs in an unbiased manner.
That's what I'm asking.
Yeah. So it's fairly involved, but there are ways to do this, which says discard those items. So let's say for a single item, I'll explain for a single item. Maybe it's easier to extend to multiple items. Let's say you have enough log lines. Let's say 45 million log lines, right? Like for this Yahoo data set. What you do is you recommend one article. If that was the article that was really shown during the experiments, you can see whether there was a click or not a click. If it was not shown, just discard that line. This entire evaluation is discarded, and then you keep moving to the next task. You get a new user, and you have to recommend a single article. If that was exactly the same article that was recommended in the log, then you can see a click or no click. If it is not, again discard this line. And if the log was collected by randomly choosing among these articles, instead of having an intelligent algorithm choose, if you randomly choose, there's a good chance, or there's a 1 in number of items chance that your prediction and the log's prediction will match. And only then do you count the feedback. Otherwise, you don't count the show, which is the experiment, nor the feedback. So out of 45 million lines, if you split across 30 articles which are always available, and the list was like, total was 300 articles, you can now get 1 over 30 number of times 45 million interactions. So this is for the single item, and similarly, you can do this for multiple items as well. Yeah.
When you're hallucinating selections, you try to choose some particular selection that minimizes uncertainty. Do you do it just randomly? And if you go through all of the selections, is it real time?
It's real time, but also we are not hallucinating selections, just the feedback. So when you're building up the list,
But you're hallucinating feedback from particular selections?
yes, for the particular selection.
So you go through all of the selections and hallucinate feedback from each one?
No, let's say you're building up this list, right? So if you were to build up the list completely, then you have to select from all possible lists of size 10, right? Instead of doing that, what we do is we pick the first element that is possible. Now we say that I don't know the feedback for this, but the current mean for this feedback, my estimated mean, what I expect is this. I'm going to give this back to it. What it does is discourages similar items to be picked. You don't want 10 Harry Potter books, well, it's not there, but 7 Harry Potter books in the top 7, right? You want a Harry Potter, because you do not know the user yet. Maybe he likes fantasy, but that doesn't mean you will show him all 7 or, 25 Die Hard movies, right? So you want to increase diversity in your results. So by doing this hallucination of mean, what we are achieving is that you have more diversity in your recommendations, and hopefully if the user doesn't like the first few, he at least has a chance to like something else. If you're completely wrong about this person liking Harry Potter, for instance, you at least are hedging your bets. That's why we do this mean hallucination. Yeah, this one.
Can you extend the hallucination to considering the whole distribution as you kind of have that?
Sorry?
You have a Gaussian distribution, right? Could you just like average across all possible feedback from the Gaussian instead of just taking the mean? Can you repeat the question?
So he's asking if I can average over all possible feedbacks instead of just assuming the mean, right?
Yes.
But for the Gaussian, if you average over all the possible feedbacks that are currently available, it will still be the mean, right?
Even for the other points you consider...
Oh, no, it's not other points, for this point.
Yes, for this point, but for the other points where you go in the next step and select the next point, the uncertainty will depend on the result you get from the first
Correct.
one, right? And this one, if it's very high, for example, then it might kind of increase your uncertainty there as well, or kind of shift the curve there.
So you're saying instead of hallucinating the mean, can I sample from this Gaussian at this point.
Yes, or even, yeah, if there is no closed form.
Yeah, you could sample. I think that would also work, but because it's still going to be an unbiased estimate of the feedback for this item.